Hi, welcome to another video. So in this video, we're going to talk about the quadratic formula. We're going to talk about how to use it. I'll give you a very nice way to set up the formula. That way you can do the same thing every time, get a process for it, and how our solutions should look when we finish up the idea of the quadratic formula. So we're going to continue. We're working on quadratic equations. We're setting them equal to 0 to find the x-intercepts, and that's exactly what the quadratic formula does. It does the same thing that factoring does the same thing that the square root method does the same thing that completing the square does, except that it works all the time. You see, the square root method only works some of the time. If you can somehow find part of your function with all your x's raised to the second power and you can solve for a constant on the other side, take a square root and you're good to go. Factoring only works some of the time over integers. Well, the completing the square method works all the time, but we found out in the last video that, man, it can be brutal. And so what we did is we learned that the quadratic formula is sort of completing the square universally all the time. I proved it in the last video, and that's what we got out of it. So I'm going to show you exactly how to use it. I'm not going to go through the proof again because we've already done that. This is more just an explanation of how this stuff works and what we should be getting at the end of the quadratic formula. So let's take a look at our first function. F of x equals 3x squared minus 5x plus 1. This is, of course, a quadratic. It is a parabola. We can tell it's upward opening because our a is positive, and it's a little bit narrow or has a vertical stretch to it because our a is more than 1. And so what we're going to do is we're going to look at this throughout the lens of how do I find x-intercepts with this. That's the only thing that the quadratic formula ever does, is finds x-intercepts for you or forces it to factor. That's kind of what we think of this as. So if we're going to find x-intercepts, the way we do that with every function ever is to set this thing equal to 0. Now, if there's one thing that you've heard me say over and over and over again is when we set up a quadratic to solve it for x-intercepts, and we're going to use the square root method, or we're going to use factoring, or we're going to use quadratic formula, even completing the square, we want everything on one side, which it's going to be if you have this set equal to 0, in order, which means that we want our exponents of our terms to be decreasing, which it is, and we want the first term positive. Let me be very specific here. With the quadratic formula, you don't necessarily have to have your first term positive, but because you're dividing by a, if that a is negative, it leads a lot of students to not quite understand what to do with that negative expression, that negative part of your fraction here, your denominator. And sometimes we get some sign errors. So I'm going to tell you that because we use a twice in this formula, and because sometimes it leads to sign errors, I'm going to have us avoid that. So the idea behind solving any sort of quadratic for x-intercepts is set it equal to 0. Get everything on one side, get it in order, get your first term positive, and try the easiest things first. See if the square root method will work. It's not going to. There's no way for us to isolate a power 2 with all of our x's inside and a constant on the other side. We'd have to use completing the square to get that. And I don't want to do that. Then we try factoring. You spend about 10 seconds trying to factor. See if we can find two numbers that add to -5 and multiply to 3 times 1, to multiply to 3. That's not going to happen, but we've checked it. We've checked completing the square. We've checked factoring. And if those don't work, in general, we just go directly to the quadratic formula. I mentioned this a few videos ago when we did completing the square that it's very useful, but for x-intercepts, there's a better way to go about it because this is found by completing the square in general. So here's how it works. Once we have this on one side in order, first term positive, we've checked the easy techniques, the square root method and factoring. We identify an a, b, and a c from our equation. Our a is always the number in front of x squared. Our b is the number in front of x, those are coefficients, and our c is the constant, and they go with the sign. So here's the way that I do the quadratic formula every time. I've been doing it this way for years. It works really well. I create a pattern for myself. So what I'm going to do, just like Taylor Swift has a blank space, we're going to put blank spaces in for every single one of these variables. And I have a pattern that I've made up for myself, like you should, to fill it out. So what the quadratic formula really looks like before we start filling things out, it has some blank spaces for all of our coefficients. And we just need to know what to do with our numbers, where to put our coefficients and our constant. So this really is the quadratic formula without any numbers plugged into it. Why we use parentheses and why I like this technique is because hopefully we understand that parentheses maintain two things. They maintain signs and they maintain operations. So when I have 4 times A times C, parentheses show that, but it also lets me put the sign in there and not accidentally lose anything, especially with our negative or a negative B. If that's a negative, we want to make sure we have both of those signs. So I start filling out the quadratic formula by using parentheses for all of our letters, all of our variables. And then we go through and we say, all right, what is our A, what's our B, and what's our C? Our A is 3, our B is -5, and our C is 1. So how I do this, you don't have to do it my way, but create a pattern for yourself. Here's what I do. I put my B first. And so what I do is I say, all right, I know that my B is my first 2 spots, my A is my second 2 spots, and C is only 1 spot and it goes last. So I fill this out by saying -5, 3, 3, and 1. And I do it the same way every single time. Create for yourself a pattern on how you want to do it. For me, that works really well. I know my B's are together, my A's are second, and my C is last. Works well. After that, honestly, it's just a matter of not making sign errors. We have some simplification that we're going to have to do occasionally, but for the most part, it's plug the numbers in and just simplify. So when we do that, we know the opposite of -5 or -5 is 5. Inside of our square root, whenever you square a number, whether it's positive or negative, you are going to get a positive number. So your first value inside of your square root will always become positive. And then just be careful right here. With this, there's where a lot of sign errors happen. If you ever have a negative in here, and if you follow my technique, there should only be one negative because your A should be positive based on the fact you got on one side in order first term positive. This should always be a positive number. This one may or may not be. So in this case, it's positive, which means you're subtracting a positive number that's subtracting 12. I'm going to write that. I'm not going to try to do it in my head because that's where my mistakes come in. So we've done that, and now there's just a couple more steps. What we're going to do is we're going to subtract 25 minus 12 is 13. And then we're going to write this as 2 solutions after we check to make sure that we have simplified it. So what do I mean by simplified? Firstly, you want to check to make sure that your square root can't be simplified anymore. There's no perfect squares as factors inside your radicand. In the quadratic formula, we call that something specific. We call this little piece the discriminant. I'm going to mention it right now just so we get it out of the way. What the discriminant does, it tells you whether you're going to have 2 real solutions, 1 real solution, or 2 complex solutions. And here's how it does it. You're going to watch this for the next 5 examples. If the discriminant, the inside part of your radical, if that's positive, we're going to add it and we're going to subtract it from whatever our B is. That's going to give us 2 solutions every time, 2 real solutions if this number is positive. If this number in here is 0, so if your discriminant is 0, well, you would add 0 and you'd subtract 0. Oh my gosh, this is the time where we get the same solution twice. We'd have 5 plus 0, 5 minus 0, both divided by 6. You get 5 6 if this discriminant was 0. So if your discriminant is positive, that gives you 2 real solutions. If your discriminant is 0, that gives you 1 real solution. Notice there's no i's, no imaginary part of this. If this discriminant is negative, square root with a negative inside of it gives you this I, gives you an imaginary or a complex solution. And so if our discriminant's negative, you'd add and you'd subtract this complex, this imaginary number, and so you'd get 2 solutions, but they'd be complex. And that would signify that you don't have any x-intercepts. So again, discriminant, if that's positive, you've got 2 real solutions, 2 x-intercepts. If that's 0, you have 1 real solution, 1 x-intercept. That's where the vertex would bounce off the x-axis. If that is negative, you're going to get an I, and it says you completely miss the x-axis, either above or below. And that's what the discriminant means. That's what we use it for, to just check how many solutions we get and whether they're x-intercepts or not. From here, we can't simplify that square root. The only thing that we can do is show that this is really two solutions. So we'd say this is 5 plus the square root of 13 over 6. And also we get 5 minus the square root of 13 over 6. If you watch that completing the square video, these look very familiar because that's almost exactly what we get with completing the square, the same look. They look so similar because the way I proved it, this quadratic formula comes from completing the square on this piece right there. And so that's why they look very, very, very similar. I hope that makes sense. I hope you're understanding the process. The process is set your function, your quadratic, equal to 0. Try the square root method. Try completing this. Try factoring. After you've got everything in order on one side, first term positive, and then if those two things don't work, then try the quadratic formula. We pretty much skip over completing the square unless you have a really, really easy one. Easy ones would be like, we don't have any easy ones up here. We'd have x squared plus an even b plus whatever constant. That would be called an easy one. That'd be fairly quick to do if you understand completing the square well. If not, just go directly to quadratic formula. Okay, let's try the next ones. So with our quadratics, we know that what we do to find x-intercepts is we set this equal to 0. So we're going to do that. But at the same time, we also want to make sure that this fits our model. Our model says we want things in order. We want things to have a first term positive. It will always be on one side if you start with function notation like we have. So when we're doing this, we go, yeah, you know what? I know I'm going to have this equal 0. But I'm also going to distribute because I want to be able to find an A and a B and a C, and that only happens if we have our quadratic in standard form. So we want things in order on one side, first term positive, so that we can identify our A, our B, and our C. Don't distribute to the -1. So in our case, we distributed, we have this on one side, it's already in order, that's fantastic, and our first term is positive. Now we would check the square root method. It doesn't look like it's going to work because we don't have something raised to the second power that contains all of our x's and a constant on the other side. There's no way to make that without completing the square. We don't want to spend the time to do it. So we're going to check factoring. Are there any numbers that add to 6 and multiply to -3? I'm not thinking of any. So if I'm not thinking of any, we're going to go directly to the quadratic formula. We need to identify our A, our B, and our C, and we just plug it into the quadratic formula. We evaluate it. So how we evaluate, create for yourself some sort of a pattern on how you like to do this and do the same way every time. So I've created some blank space, and I'll write your name. And then we're going to plug in our A and our B and our C. So what I do, I plug in my B first. I know my A is 3, my B is 6, my C is -1. I'm going to put the B's first, A's second, C last. As I mentioned before, if you have this on one side in order first term positive, there should only possibly be one negative in these two numbers right here. A would be positive if you followed my technique. So this is going to be the only negative we have. If that number's negative, then you're going to ultimately be adding here. Be very careful with that. It's very common for students to go, oh, it's 36 minus 12. It's not going to be minus 12. It's going to be plus 12. Be very, very careful. So now it comes down to simplification. We know that x equals -6. There's no sign change there. We just have negative whatever that number is. Inside of our square root, this discriminant, this is going to be 36. And then because we're subtracting a negative, we're subtracting -12, that really is an addition concept. This is the one mistake that students make time and time again, is they go so fast, they try to do everything in their head, that they don't catch that. Be very careful. If it takes you writing this out as 36 minus -12 to understand that you're going to be adding here, that's fine. Either way, but just be very careful on that. All over 6. So we continue simplifying. I know that the -6, that looks really good. That's fine. And then the square root of our discriminant is now 48. You know what? You should be able to tell right now whether this parabola, that is a parabola, is firstly opening, and it is. And it's a little bit narrow. It's got that coefficient of 3 out there for our a. Whether this is going to cross the x-axis or not. By looking at your discriminant, we should be able to immediately identify that and say, hey, that's 48. That's a positive number. I'm not getting any i's in it, but I'm going to be adding and subtracting it. So that is not 0. It's going to be -6 plus some sort of real number, and -6 minus some sort of real number. That's going to give me 2 real numbers, 2 real solutions, 2 x-intercepts. If your discriminant is positive, you are crossing the x-axis twice. But there's a little bit more work for us to do. You see, we can't leave the square root of 48. And if you give this as a solution, it's not technically wrong, is it? But it's the same thing as if you left a fraction 2/4. Well, no one's going to really like that. People are going to want this to be 1/2. 2/4 is 1/2. The same thing happens here. We need to simplify to the most simple form so that people can identify it a little bit better. So how that works, we take off our square root, and we try to simplify by finding a perfect square factor. So, and the biggest one that divides 48. So we think 48, I'm not thinking 4, even though the square root of 4 is 2. I'm thinking 16. So the square root of 16 is the biggest perfect square that divides 48. In fact, it's 16 times 3. So when we simplify that, the square root of 16, that's great. We can simplify to 4. The square root of 3, yeah, we can't simplify that, so it stays as 4 square root 3. And so we have this x. I showed this to you in another video that we can continue to simplify. It was in the square root method if you want to check that out. But here's the way that this happens. If you can factor these two numbers, then you can, and simplify with this, then that's possible simplifying. If you can't, then don't do it. Here's what you may never do. Don't ever just cross out these two numbers. That doesn't work. What actually does work is if these values, 1, 2, and 3, if they all have a common factor, then you can simplify that. And the reason is, if you can factor a number out of here like 2, if you can factor it, hey, now these are connected by multiplication. We know that we can simplify factors when they're connected by multiplication like that. We would get -3 plus or minus 2 root 3 over 3. You can get the same thing, but you've got to divide all 3 of them. Not this one, but these 3, coefficient and factor and constant. So if we divide all of these by 2, -6 divided by 2 is -3. 4 divided by 2 is 2. 6 divided by 2 is +3. And we get the same thing. We get that this would be -3 plus or minus 2 root 3 over 3. Either way you go, I really don't care, but you do need to understand that you can't simplify just one part of that. That's not okay. From here, man, we just write this as 2 solutions. We know they're real. There's no imaginaries. We know there's 2 of them. There's not a 0 here. So we understand that these are x-intercepts, and if we wanted to approximate on a calculator, it would tell us about where on the x-axis this parabola is going to cross twice. That's about all there is. Those are 2 x-intercepts, and that is all the quadratic formula ever gives us. It just tells us where this quadratic has x-intercepts if it does. If your discriminant is positive, you're going to have 2 x-intercepts. If it's 0, you're going to have 1. That's where the vertex is. And if it's negative, as we're going to see in about 3 examples, then you're not going to have any x-intercepts at all. You have complex solutions. All right, let's try this next one. So I was talking to Taylor Swift on the phone the other day. That's a lie. And I said, listen, I really like my 2 favorite songs for math. And she was like, what favorite song is that? I was like, oh, you know the ones you wrote about evaluation of functions? And she's like, oh, right, blank space. I was like, yes, that's absolutely right, because that's how I do quadratic formulas with that blank space. You go, I got a blank space, baby. I'll write your name. Except instead of name, we write our A, B, and C. But she also has another one. I don't know if you know it, but it goes like this. It's never, ever, ever, ever plug in fractions to the quadratic formula, ever. I said, that's brilliant. She goes, oh man, that's the original way I wrote the song, but I didn't think it would fly. I was like, T.S., I know you're musically inclined and all, but I disagree. Like, I think that would have been awesome. She was like, totes. I don't know what that means personally, but I think it was like agree with me. And then I said, yeah, you should re-record it. She's like, I just can't. It's like licensed now, and it's like copyrighted or whatever. It's like bummer. But it's great for understanding the quadratic formula. Don't ever plug in fractions to the quadratic. That was a little bit dramatic. I'm sorry about that. Don't ever plug in fractions to the quadratic formula. While mathematically possible, it makes your work 10 times harder. Don't do it. Instead, we know something about fractions. We know that if we multiply both sides of an equation by the same number, it keeps this equation equal. It keeps it exactly what it was. We also know that we can multiply by an LCD and it will kill off all your fractions. That's brilliant. So while we can't do it here, we can't just get rid of that fraction. That was the drawback of the completing the square method. If you remember that, we had lots of fractions and they were horrifying. So instead of having to do that, why don't we just use the quadratic formula? Why don't we set this equal to 0 like we would do for every finding x-intercepts technique? We have this in order. We have the first term positive, but before we do anything with it, before we even check for square root method, by the way, it won't work here. Before we do factoring, it wouldn't work here anyway, but we wouldn't check with a fraction anyhow. Before we even think about completing the square, and we actually did that problem in completing the square, we're going to get rid of all our fractions. Especially if you do quadratic formula, get rid of your fractions. Find your LCD. In this case, it's 2. Multiply both sides by that 2. Distribute it, it's going to get rid of all your fractions. So we'll get a 6x squared plus 2x, don't forget that, minus 1. 2 times negative 1/2 is negative 1, we write minus 1. On the right-hand side, you still have 0 because 0 times any sort of number is going to give you 0. This is so much easier to work with. I don't care what you're doing, do this first. So if you're setting functions equal to 0 and solving them, get rid of your fractions first, multiply by the LCD. This is way back to like intermediate algebra sort of stuff. This is what we do all the time, is get rid of our denominators by using an LCD on both sides of an equation. From here, everything works nicer. So if you wanted to do the square root method, it'd work better here. Even completing the square would work sort of work better here. You wouldn't have one fraction for a while. If you want to do factoring, it would definitely work better here if it was factorable. Now we would try, but there's no numbers that add to 2 and multiply to negative 6. We can't do that. So when we do quadratic formula, this is even nicer. Don't ever plug in fractions to the quadratic formula, like ever. So we know that this is one side in order, first term positive. We got rid of our fractions. We have an A and a B and a C. Well, we're going to plug these into the quadratic formula because that's really our last and best choice. And so we're going to find our A, which is 6, our B, which is 2, our C, which is negative 1, and we're going to plug them in. So B comes first, I put 2 and 2. A is next, I put 6 and 6. C is last, I put negative 1. I'm really careful here. I understand in my head that that's a negative, so I'm going to be adding. Be very careful. Again, if you do this, if your first term's positive, like I've told you to do, then the only number that can be negative here is that one. That will change this to an addition and not a subtraction problem. That's why we come with a technique, isn't it? So we can do the same thing every time and not run into mistakes when we don't expect them. So negative 2, no problem. Plus or minus, we got it. 2 squared is 4. We already determined this, but we're going to be subtracting a negative. That's going to be adding 24. All over 12. We keep on simplifying. That's 28. We're going to have to simplify the square root of 28. We're looking for the biggest perfect square that's a factor of that number, so we can take the square root of it. In this case, the biggest perfect square that divides 28 is actually 4. So if we simplify that square root of 4 into 2, we can't simplify the square root of 7, it stays there. What we get is this -2 plus or minus 2 square root 7 over 12. You should be answering in your head right now whether this parabola, and it is a parabola that's upward opening, a little bit narrow, has one x-intercept, 2 x-intercepts, or no x-intercepts. Your discriminant will tell you that. Right here it will tell you that. That number is positive. This is going to give us 2 real solutions and therefore 2 x-intercepts where this parabola crosses twice. All we're going to do now is simplify it. 2 ways you can go. If you want to factor out 2 and simplify 2 with 12, you're going to get a -1 plus or minus 1 square root 7 over 6. Or you can divide all 3 of these numbers by 2. 2 divided by 2 is 1 and 6. We would never write 1 root 7. It's like writing 1x. It's implied that there's a factor of 1 out in front of that. So we don't really need that. All we've got to do now is understand these are 2 real solutions. We're going to write both of them. So our -1 plus square root 7 over 6 and -1 minus square root 7 over 6. If you need an approximation, be careful on your calculator. The best way I found to do this is put a parentheses, put -1 plus square root 7 end parentheses, and then press divide by 6. And then same thing, parentheses, -1 minus square root 7 end parentheses, divide by 6. And it'll give you a nice approximation all at one time. Let's go on to the last one. Again, we see some fractions. It is a quadratic. It's quite wide, isn't it? Because we have that 1/8 in there. That 1/8 says you have a vertical compression. It's widened out this parabola. We'd have a y-intercept of -2. We're going to start talking about that. I'm prefacing another section for us. But let's go ahead. Let's see if we can set this equal to 0. If we can get everything on one side in order, first term positive, kill off our fractions, and then see if we can use an appropriate technique. Right now, you should be trying that. So here we go. Whenever we want to find x-intercepts, and that's what the quadratic formula does, we're going to set the function equal to 0. So in our case, we've got that on one side. We've got it in order. Can you see it? Can you see the in order? X squared, then x, then a constant. We have the first term positive, which is great. That's what we want. We want to set that up. Even if you start off with a negative first term, remember that once you set it equal to 0, it doesn't care whether you have negative first or you change all your signs. X-intercepts don't change when you reflect a function about the x-axis. So if we set this equal to 0 and change all our signs, yeah, it's going to look like the parabola reflects itself, but the x-intercepts don't care. And that's one nice technique we can use to make sure the first term is always positive. Very nice. Okay, so we have it in order, first term positive, no problem. The fractions are going to kill us, man. We don't want fractions here. Fractions are horrifying to plug into the quadratic formula. We definitely don't want to do factoring. We don't factor with fractions. Don't do anything with fractions in equations. Get rid of them. And so we have this equation with 0 on one side. Use your LCD. In this case, it is 8. Multiply both sides by 8. Distribute the 8, and then simplify your fractions. So we would get x squared, the 8 and the 1/8 are going to give us 1, minus 2x. 8 times 1/4 is 2. Minus 16, do not forget that you need to distribute that. 8 times -2 is -16, we write minus. And then 0 times 8 is 0. So we're showing that because that's valid, right? We need to make sure we multiply the same thing on both sides of our equation. That's how to use the LCD to get rid of your fractions. But 0 times any constant is going to, 0 times anything is going to give us this 0. Well, now we're ready for it. So the first thing we check, man, does the square root method work? And it doesn't. We can't get a power 2 isolated with all of our x's on one side and a constant on the other without doing the special technique of completing the square. We don't want to do that. Second thing, we try factoring. Can we think of anything, man, it kind of looks like it at first glance, that adds -2 and multiplies to -16? Remember that that have to be different signs there. 16 and 1, no, that doesn't make -2. 8 and 2, no. 4 and 4, no. So there's nothing that's going to factor for us. Now is our time to use a quadratic formula. So we're skipping completing the square, even though it might actually be kind of easy here. Because the quadratic formula is it's like fail-safe. You just plug in your numbers and you go. So our A is 1. Don't forget that there is a coefficient in front of x squared. Our B is -2. And our C is -16. That's what we're going to evaluate into our quadratic formula. So we know that now. We're going to do our B first. So our B is -2, -2. Our A next, that's 1 and 1. Our C last, that's -16. I'm noticing right now that's a negative number. That's the only thing that can possibly be negative here because we have our first term positive all the time. That means that we're going to add this yet again. So I'm going to be very careful because we have some sign changes here. Opposite of -2 or -2 is +2. Instead of our square root, be careful. -2 squared is 4, not -4. It's very easy for students to make little sign errors. We're not going to be subtracting 64. We're going to be adding 64. And lastly, 2 times 1 is 2. Kind of on the home stretch here, we're going to combine 4 with 64. Man, right now you got to be seeing that right there is a positive number. That's 2 real solutions, 2 x-intercepts. We're just going to simplify them to make them a little bit easier. So, oh man, what goes into 68? Looks like 17 goes into 68. (17) and 4. So 4 is a perfect square. 4 times 17 is 68. Let's simplify it. So the square root of 4 is 2. Square root of 17, yeah, you can't do it. It's a prime number. There's no perfect square in there that we can even factor out. That's why we chose the 4. And then we're going to rewrite this a little bit. And we are almost done. All we've got to do is simplify. So whether you factor the 2 out and then cross out the 2 that you're going to factor, like that, factor it out, you'd have a 1. Factor that out, you can have a 1. 2 simplifies with a 2. Or you'd like the other technique of, hey, let's just divide 3 numbers by the same thing. So divide them all by the greatest common factor they all 3 have in common. 2 divided by 2 is 1, and 1, and 1. Whatever we're going to do here, we're going to end up with 1 plus or minus the square root of 17. We already talked about the discriminant, but now we can really see it. There's no I here. We're adding and subtracting something that's not 0, so we are getting 2 distinct solutions. They happen to be real. And that is exactly where this parabola, that's a very wide parabola, is going to cross the x-axis. Those are your zeros or your roots. One thing that I want to say is those are called exact solutions. So even though they don't make a lot of sense to us as far as a decimal number, because they're not a decimal number, we'd have to approximate to get that, this is called exact. When you start evaluating on your calculator what 1 plus the square root of 17 is and gives you a decimal, that is actually an approximation. The square root of 17 goes forever. It doesn't repeat for any length of time. It's not a fraction. It's an irrational number. And so we can't write it as a decimal and contain all of its information. The square root of 17 contains all of that information. That's why it's called exact. The approximation, when you say, oh, my calculator says this, I'm going to round it to the blah decimal place. Well, you've just rounded it, haven't you? I mean, you've cut off a big portion of that number. That goes forever. That's an approximation there. So keep that in mind. This would be an exact form of your solution. Also, one more thing, that this is going to look very strange, but keep in mind, these are x-intercepts. So what this really is, this is a point. This gives you a point on the x-axis, x comma 0, because you are on the x-axis. The same thing for all of these. These are all points, and they will look very strange to write. But this point would be negative 3 plus 3, 2 root 3 over 3, comma 0 as a point on the x-axis. It's kind of weird, but that's what this is giving you. It is x-intercepts. I need that to never leave your mind. So we're going to come back in just a second. I'm going to give you 2 more examples talking about when imaginary zeros happen, how to change a sign if your first term is negative, and then where your discriminant of 0 would come in. So I'll be right back. All right, last couple problems. So we're looking at 2 more quadratics, just some special things that I want to talk about. We already know about the discriminant, that if the discriminant, the inside of that radical, when you're doing the quadratic formula, if that's positive, we get 2 real solutions. I'm going to show you when you would get 1 real solution. I'm going to show you when you would get no real solutions. And also on this one, if your first term is negative, how to deal with that and make the quadratic formula work just a little bit better so you don't have to divide by a negative. In either case, we're going to set this equal to 0 like we do every time we're trying to find x-intercepts. And we want to make sure it's on one side, of course it's going to be. We set it equal to 0. In order, it is in order with the first term positive, and that's true. Then we would try the square root method. It doesn't work. Factoring, it actually would work. It would work here. Factoring works very well if you have a discriminant of 0. Most of the time, it's going to work fine. And so sometimes we don't make it that far. So I'm going to show you if we didn't see the factoring or if we just didn't want to, that the quadratic formula would give you the 0 of a discriminant, and that's exactly what that means. So our A would be 9. Our B is negative 6, and our C is 1. Let's plug that into the quadratic formula. Maybe we missed the factoring or something. So the first thing we're going to do, I'm going to think my A is B, my A is 9, my B is negative 6. My B comes first. My A is next. My C is last. Right now, I'm seeing that these are positive numbers. I'm going to be subtracting 36, not adding. Opposite of negative 6 is 6 plus or minus the square root of, we'll have a positive 36 minus 36, and we see the 0 right there. So we end up getting 6 plus or minus 0 over 18. And here's what we were talking about a long time ago. What happens with a double root, or something that would factor as this expression squared, it has what's called a multiplicity of 2. We talk about multiplicity a little bit later. And that multiplicity is this idea of a repeated root, a repeated factor. And it tells us something about this. It tells us that on that particular x-intercept that comes from that factor, you're going to be bouncing or touching the x-axis, but not crossing it. And this is what this says. If the discriminant is 0, you will be bouncing or touching off the x-axis. In this case, because we only have one turning point, a parabola can only turn one time. That turning point, that vertex, is going to be touching, right, sitting on, bouncing off of the x-axis at exactly this value. You see, we get the same solution twice. That 18 is the only number you can add and subtract from another number to get, it's called additive identity. You can get the same number back, whether you add it or subtract it. That's 1/3, and again 1/3. This is the only real solution, is 1/3. It's not imaginary, there's no I in it. There's not 2 of them though, so this is the only time that you would get 1 x-intercept and 1 real solution from right there, if your discriminant is 0. That's what that tells you. I just want to make sure I reiterated that one more time. All right, last one. We have something that looks kind of nasty. It's in order, but when we set this equal to 0, everything's negative, and especially that, we don't mean negative, everything's negative, but especially the first term is negative. That really hurts for factoring. That's not so great for the quadratic formula. And so when that happens, let's divide everything by a negative. Let's make sure our first term is positive. The reason why is because where the a sits on your quadratic formula is on the denominator and also in here. So if this is negative, it starts messing with our signs inside our discriminant, can screw us up. If this is negative, it really starts messing with our signs of a fraction. So when we change our a from a negative to a positive, we eliminate two negatives inside of our function. And it sets it up better for factoring if we can factor it. That's why we do it. So it helps us with sign errors. Sign errors are the #1 mistake in math, in my experience. I've been doing it 15 years now, and even through Calculus 3, like 90% of the errors are sign errors, just little teeny mistakes that we're making. So this is one way to avoid it. So what we're going to do is we're going to imagine either factor a negative out, no problem, or add everything to the other side, no problem, or divide everything by -1, including the 0, you'd still get 0. Either any one of those things. Ultimately, what's going to happen all of our signs change. Just make sure if you're changing the first sign, you're changing all the signs. That's important. Now, we try square root method, ain't gonna work. We try factoring, that's also not gonna work. There's nothing that adds to 1 and multiplies to 16, 4 times 4. But the quadratic formula always works. We really wouldn't want to do completing the square here. Can you imagine that? You'd have to hold this number back, you'd have to divide by 4, you'd have to find half of that, that's 1/16, then square it, that's 1 over 256, then add it, and then factor it, and then subtract, and then divide, and then take a square root plus and minus, and then subtract again. That's a wreck. The quadratic formula does it for us automatically. So with our a being 4, our b being 1, and our c being 4, we can plug this in very nicely. There's no negatives, there's no fractions. That's great. We don't want any of those things. No negatives in our a especially. And we create some blank spaces for all of our coefficients and our constant. We're going to plug these in using whatever pattern you feel most confident with. For me, I like to look at my b. My b is 1, my a is 4, my c is also 4, and it goes last. That's really quick, that's really easy, it's very efficient. That's speed with accuracy. Then we start simplifying. -1, no problem. I know that's going to be -1 plus or minus the square root of, I know I'm going to be subtracting here because none of these numbers are negative. So when I square the 1, I get 1. I subtract 4 to the 3rd power is 64 over 8. And I'm going to be very careful. 1 minus 64 cannot be 63. It's -63. That negative is very important. It's the difference between your parabola, which is actually downward opening, crossing, and completely missing. Now, I said something important that's got to sink in. This parabola decidedly is downward opening, and it's narrow because it has this vertical stretch. The absolute value of a is more than 1. It is being stretched out. It's downward opening, but it's not going to cross the x-axis. When we change our signs, you might be thinking, wait a minute, that's upward opening. You screwed it up. I might have screwed up the look of the parabola if we were actually graphing this, but we're not. We understand that is our parabola. This is just a way to use the quadratic formula better. And what's the quadratic formula give you? X-intercepts. That's it. So if that's the case, when you take a parabola and you start reflecting it about the x-axis, the numbers on the x-axis cannot change. Reflection about the x-axis takes y values and changes their sign. Well, the y value of an x-intercept is 0. Changing the sign of 0 doesn't change the x-intercept. And that's why we can do it. We can change the sign of this right here and not affect the x-intercepts. And that's all we care about for the quadratic formula. That's why we can do it. So x equals this -1 plus or minus square root of -63 over 8. We got our sign right. And right now, we should understand what this is telling us. The discriminant is negative. You are going to get an I. Man, if you don't have an I, you're not seeing your problem very well. You're welcome. We have to be able to see that this is going to give us an I. Right there, if your question says how many real solutions you get, you say 0. There are no real solutions here. How many x-intercepts are you going to have? None. This is not going to cross the x-axis at all. It's not even going to touch it. What we do need to do, if you're asked for complex solutions, we do need to simplify it. So we're going to think about this. We're going to pull out that -1 because that's the value that gives us I, times, let's see here. 9 is the largest number that we can take a square root of that divides 63. And so this is going to give us square root of 9 is 3. Square root of -1 is I. Square root of 7 is the square root of 7. That's how that simplifies. So we're going to have this x equals -1 plus or minus 3i square root 7 all over 8. We cannot simplify that at all. This is in the proper order. We like coefficient, then I, then square root where appropriate. But we are going to write this as two solutions, two complex solutions, two non-x-intercepts. Now, can you give me an approximation for it? No, our calculators, we can't really find a value to approximate this as on a number line because this doesn't go on a number line. There are ways to show, to graph complex numbers, but not on an XY axis because that is a real number line in both the vertical and horizontal directions. So this is it. This is as good as we can get to represent that this parabola, which is downward opening, completely misses our x-axis. I hope that makes sense. I hope I've illustrated a nice way to do quadratic formula, talk through the very specifics of what it is that you are doing and how to best approach that. So hope that made sense. I'll see you for the next video when we talk about intersections of functions, how to set them equal to find out where they cross each other, which is kind of interesting. See you for that.